All right, back again. And where we left off last time was actually, I was just about to reiterate a point I made in working out the last problem. And that is just a reminder that when the action is occurring at an incline relative to the way we normally define the axes as being X horizontal and Y vertical, if it's inclined at an angle like it was in the last problem, then the equations for the X and Y components switch places. That is, the sine and the cosine switch. The X component will be the sine and the Y component will be the cosine. And so say the Y component of weight will be mg cosine theta. Watch out, because the book actually for some reason switched this to sine at the last minute. So the last equation in that series is wrong in the book. It's cosine theta for Y and sine theta for X if it's on an incline. Another example of something on an incline would be this example here, where you've got you're using a force of 150 newtons basically to try to push a safe up a ramp. And the 150 Newton force is being exerted parallel to the ramp in an upward direction to try to get the 250 kilogram safe into the truck. And the angle of the ramp is 17 degrees to the horizontal. And so we're wondering, what is the acceleration of the safe if there's no friction? And what is the acceleration of the safe if friction is equal to 120 newtons? Okay, in this case, this is a little bit different from the skier, because in this case, both the friction and the X component of the weight are working against the motion, because we want the motion to be up the ramp this time, not down the ramp. So we're trying to push it up the ramp. The X component of the weight wants to push it back down the ramp, and friction is resisting whichever direction we want to push it in. So friction is pushing down the ramp also. So a little diagram here. I think I put a little too much effort into the truck and not enough into this part of it. But anyway, hopefully we can see. You've got a ramp that's at 17 degrees to the horizontal. You've got the safe, and I kind of missed the center of gravity of the safe a little bit, but you've got the normal force going up from the safe, which is perpendicular to the ramp. And you've got the weight, which is this force right here, which is going straight down towards the center of the earth. And it's, again, it's the Y component. We've defined the axes so that X is parallel to the ramp and Y is perpendicular to the ramp. It's the Y component of the weight that balances out the normal force. And the X component of the weight is pushing down the ramp. That's what this little WX is that you can hardly see there. It's the X component of the weight pushing down the ramp. The force, though, is pushing the safe up the ramp. At the same time, friction is also trying to push it down the ramp. So those are the forces we're dealing with here. The X component of the weight is, again, because this is on an incline, the X component of the weight is going to be mg sine theta. So that's 250 kilograms times 9.8 meters per second squared times the sine of 17. That's 716 newtons. The Y component of the weight is going to be mg cosine theta, and that's 250 kilograms times 9.8 meters per second squared times cosine of 17. That's 2,343 newtons in the Y direction. The X direction is the only direction we have to be concerned with in terms of acceleration, because again, as I said, the normal force balances out the Y component of the weight, and so there is no acceleration in the Y direction. The net force in the X direction is going to be equal to the mass times the acceleration in the X direction. Or in other words, the acceleration in the X direction is equal to the net force in the X direction minus or divided by m. In this case, the let me see here. The force that you're exerting on the safe is 1150 newtons. So that's 1150 newtons in the direction we want the safe to go. And opposing that is the X component of the weight, which is 716 newtons. Okay, and we're not considering friction in part A, so we don't have to worry about that. So 1150 minus 716 would be the net force in the X direction pushing the safe into the truck. And the mass is 250 kilograms. And when you work that out, you get an acceleration of 1.74 meters per second squared. On the other hand, if there is friction involved, then the net force in the X direction will be the amount of force pushing the safe in the direction you want it to go. That's 1150 minus the X component of the weight minus the friction, which is 120 newtons in this case. So 1150 minus 716 minus 120, that's the net force in the X direction divided by the mass gives us an acceleration of 1.26 meters per second squared. So again, there's less acceleration when there's friction involved than there is when there isn't, which makes total sense. Okay. This brings us also to the subject of tension. Tension is a force along the length of a connecting medium. Connecting medium, well, is something that connects things like a rope or a string or a chain or a cable, something like that. Anyway, in the case of tension, you're talking about connecting media that are capable of pulling something but not pushing something. So the connecting media and that we're talking about here would be flexible, and they're not able to push anything. So again, like a rope or a string, you can pull something with a rope, but you can't push something with a rope. The same with a chain or a cable, or a string, that kind of thing. The pulling force, tension is a pulling force that acts along the length of the flexible connector. And let's see, yeah, okay. So if we're talking about a person holding a mass on a rope, we can draw a little diagram of it. This is the person's arm, and there's fingers holding the string, and there's the mass that's being held on the rope, and this is the rope that's holding the mass. Of course, because this item has mass, it will be pulled downward with a force equivalent to its weight, and the total tension in the rope or the string or whatever it is will have to be equal to the weight in order to prevent any kind of acceleration in the up or down direction. So if this object is just being held stationary on a string and it's not falling or it's not rising with an acceleration, then the upward tension in the string must be equal to the downward weight on the mass. Okay, so and that's again because if the mass is stationary, then there's no acceleration, and that means there's no net force in the up and down direction, which means that the upward force in the y direction has to be equal to the downward force in the y direction. So here the only external forces would be gravity down on the mass in the form of weight, and tension upward on the mass through the rope or the string. So the net force would be tension minus weight, and that we already know is 0 because there's no acceleration in the up and down direction. Or in other words, tension is equal to weight, as long as the object is not accelerating in the up or down direction. And weight is equal to mg, so tension would be equal to mg in this case. For the mass of 5 kilograms specified in the example, if you also ignoring the mass of the rope, which is sometimes realistic and sometimes not. In this case, tension would be equal to the weight, which is equal to mg, which is 5 kilograms times 9.8 meters per second squared, or 49 newtons. That is not only the weight pulling downward, it's the tension in the rope pulling upwards. Flexible connectors are good at transferring forces around corners or around other obstacles. So like, the tendons in the body, they can transmit force from your muscles. Oh, okay, how about like this? From the muscles in your hand around the corner into your finger. That's kind of how your tendons work. Traction in a hospital, use of pulleys, or at least simple pulleys, or the brake cable in a bicycle. When you basically you squeeze the brake handle on the bicycle, you're pulling on the cable, and the cable pulls on the brake pads that rub against the wheel, and that's what stops you. But these flexible connectors can change the direction of the force, but not its magnitude. And that's why I had pulleys in parentheses here, because that would apply to a pulley system if it's simple, like a single pulley. But if you're using several pulleys and you arrange it the right way, that can actually have the effect of magnifying a force. So that would not be a case like this. So an example of tension in a wire or a rope would be, say, tension in a tightrope. When some guy's walking across the tightrope, it's going to create tension in the cable or the rope. So we want to calculate the tension in a wire supporting a 70-kilogram tightrope walker if the wire deflects by 5 degrees. This is what happens basically when you exert force on the center of one of these flexible connectors, is that the connector will deflect a little bit. In these problems, we're assuming that the connector does not stretch. Okay, so the way that the connector would be able to deflect would be that basically the poles, in this case holding it, would bend a little bit toward the center to allow the deflection to occur. In real life, the connector probably would stretch, well, if it's a rope anyway, or if it's a string. If it's a metal cable, then it probably wouldn't stretch, and it probably would deform the poles. But in order to make the problem simpler, we're going to assume that the connector does not stretch. Okay, so the deflection is 5 degrees. So the dotted line represents a line that's going perfectly horizontal. That is the original position of the connector. We're assuming that the connector was taut to begin with, that is, that it was really tight and perfectly horizontal. And so then when the tightrope walker is out at the center of it, the rope deflects by 5 degrees on each end. So this angle here between where the rope actually is and where it originally was is 5 degrees on both the left and the right. In order to draw the axes, we've got a situation here where if we look at the center of mass of the tightrope walker, we've got tension on the right-hand side that's pointing to the right and up a little bit, and tension on the left-hand side that's pointing to the left and up a little bit, and the weight of the tightrope walker, which is pressing straight down. Okay, we have a situation here where there are no two vectors that are parallel to each other. And in a situation like that, you might as well just go ahead and choose the axes to be the way we normally choose them, which is X horizontal and Y vertical. Okay. So we're going to focus on the point in the line where the walker is standing at any given moment. And the system will be the tightrope walker himself. The external forces will be gravity in the form of weight, and also the tensions in the line. Since he's in the center of the rope, well, I didn't quite draw it quite that way, but assume that he is standing in the center of the rope, and therefore the tension to the left is the same as the tension to the right. Okay, that makes things a little bit easier. And we can ignore the weight of the wire. We basically need to, unless we want the problem to become a lot more complicated. And since the tightrope walker is just standing there on the wire out in the middle, kind of showing off, we can assume that there's no net external force because there's no acceleration in any direction. A free body diagram of the situation would look something like this, where you can make things conform to the X and Y axes. The downward force is still in the negative Y direction, and that is the weight. But in the upward direction, you have the Y components of the tension to the right and the left. So TRY for the right-hand tension in the Y direction, and TLY for the left-hand tension for the Y component of it. And those would be pulling straight up in the Y direction. In the X direction, the forces would be to the right. It would be the X component of the tension on the right-hand side, and to the left, right, okay, the other right. And to the left, you'd have the X component of the tension to the left. Okay, so that's along the X axis. And again, the net force in the Y direction is 0 because there's no acceleration going on in the Y direction. And the net force in the X direction is also 0 because there's no acceleration in the X direction. Okay, what we have to do is find a value for the components of the tension in both the X and Y directions. So what we have here is a situation where, just looking from the tightrope walker to the left, we have the tension in the line to the left, and the line, of course, is deflected by 5 degrees, and it's rising a little bit to the left. So we have the Y component of the tension on the left-hand side, and there's an X component to the tension on the left-hand side. Going from the tightrope walker to the right, we have basically the mirror image of what we have to the left. So we have tension in the line going to the right, and that's deflected by 5 degrees. And we have the X component for the tension on the right and the Y component for the tension on the right. But because the net force in the X direction is 0, that's just another way of saying that the X component of the tension to the right is the same as the X component of the tension to the left. And the same would be true of their Y components too, by the way, but it's the X component we're more interested in at the moment. Okay, so we can go through some processes here and prove that TL is equal to TR, which is equal to the overall tension, as we predicted. And we can go through vertically also and prove that the Y component of the tension to the left is equal to the Y component to the tension on the right, which is equal to the overall tension, which we predicted also. And overall, this is kind of the more important part. The overall, the Y component of the tension to the left is equal to the magnitude of the tension to the left times sine of 5 degrees. And our axes are not inclined here, so notice that the Y component is back to being sine. And that's equal to just the magnitude of the tension times the sine of 5 degrees. The Y component of the tension to the right is equal to the magnitude of the tension to the right times the sine of 5 degrees, or just the tension times 5 degrees. And looking at the net force in the Y direction, that's going to be the Y component of the left-hand tension plus the Y component of the right-hand tension minus the weight. But again, that has to be 0. The net force in the Y direction is 0 because he's not falling or shooting up in the air. So the Y component of the tension to the left is just T sine 5 degrees, like we saw here. the y component of the tension to the right is T sine 5 degrees, like we saw up here, minus W. So when we combine the two T sine 5 degree terms together, we get 2 times T sine of 5 degrees, and that's equal to W. When we rearrange that to find T, we end up with T being equal to the weight over 2 times the sine of 5 degrees. Weight is mg, so that's the same as mg over 2 times the sine of 5 degrees. And mass is 70 kilograms, g is 9.8 meters per second squared, and the sine of 5 degrees is 0.0872, so that comes out to 3,933 newtons of tension in the wire. Okay, so that's a way to figure out a tension in a wire. As it turns out, the largest tension in a wire is, or any kind of flexible connector, is caused by a force perpendicular to the length of the line, as was the case in this last example. And that tension will be equal to the weight, that is the force on the line, times 2 sine theta. If the force is perpendicular to the line, but it's not in downward, so in other words, if it's a force perpendicular to the length of the line, but maybe it's sideways instead of downward, then you can look at it like this. We can call the perpendicular force F perpendicular, and the tension in the line would just be the magnitude of the perpendicular force over 2 times the sine of theta, theta again being the angle of deflection of the connector, the angle between the horizontal and the current position of the connector. The tension would be larger for, just looking at the equation, the tension would be larger for larger magnitudes of the perpendicular force, and assuming that the perpendicular force doesn't change, the tension would actually also be larger for smaller values of theta. So smaller deflections actually correspond to larger tensions. Because if theta is 0, and it's sort of the absolute limit of small deflections, if theta were 0, then sine of theta would be 0, and you'd have a force divided by 0, which is mathematically, at least approaches infinity when you divide something by 0. Tension is, so and another example could be pulling a stuck car with a line tied to a tree. That's on page 245. You can see the diagram there. They've drawn the car much more prettily than I can. But anyway, what you're doing is you've got a car that's stuck in the mud, and you've attached a line to, say, the towing hook on the front of the car, and you've attached the other end of it to a very sturdy tree that's 3 meters away, and you're going to try to move the car by applying force to the center of the line. And this technique has actually been tried, and it's well proven, and it's actually a pretty good way to do stuff like this. And every time, basically, you apply force to the center of the line, and every time the car moves forward, you retighten the line and apply some more force, and the car will move forward a little bit again. And you tighten the line and you apply some more force, and eventually the car will be out of the mud. Since the angles are small here, the tension is large, and it's transmitted to both the car and the tree. So here's the diagram. You've got your car stuck in the mud, and you've got a line going directly from the car to the tree. This distance here was originally 3 meters. But again, we're assuming that when the force is applied to the line, causing it to deflect, we're assuming that the line does not stretch. And so it's actually this distance around the deflection that totals 3 meters. This distance here is a little bit smaller because we're assuming that once the line deflects, the car moves a little bit toward the tree, or maybe the tree moves a little bit toward the car, so you better watch out below. But anyway, one of these things moves towards the other so that this total straight line distance between the car and the tree is now a little bit less than 3 meters. Okay. And I called it a rope, but actually in the diagram, it looks more like a chain. So you could kind of believe that a chain would not stretch. Okay, so perpendicular force is applied to the rope so that it's displaced by 0.25 meters, and the perpendicular force itself is 200 newtons. So what force is exerted on the car? Well, one thing we need here, as in the last example, is the angle. And in the last example, they gave us the angle, but in this example, we're going to have to find it. So there are a couple ways you could find the angle. Actually, the one we're probably more familiar with would be using the inverse tangent. Inverse tangent, theta, that is that angle, should be the inverse tangent of the y side of the triangle over the x side of the triangle. The way we've got things here, this straight up and down, the 0.25 meters is the y side of the triangle. The 1.5, though, that's the hypotenuse. And the x side of the triangle would be this side here, the one that we don't know. So before we can use the inverse tangent to find the angle, we have to find what the length of the x side of the triangle is. So we can use the Pythagorean theorem because this is a right triangle. This is a perpendicular force, so that's a right angle there. And so therefore this is a right angle. So we're doing that down here. That means x would be the square root of the, the hypotenuse squared would be the x side squared plus the y side squared. And if what you're looking for is x, that's actually going to be the hypotenuse squared minus the y side squared, and take the square root of that to get x instead of x squared. And let's see, the hypotenuse side is 1.5 meters, so you square that, minus 0.25 meters for the y side of the triangle. Take the square root of that and you get 1.48 meters. So the x side of the triangle is 1.48 meters. Theta would be the inverse tangent of y over x. That is the angle whose tangent is 0.25 over 1.48, and that is 9.59 degrees. Now that we know the angle, we can use the tension equation. Tension is just the perpendicular force over 2 sine theta. The perpendicular force we've been told is 200 newtons, and that's over 2 times the size of 9.59 degrees. So that's 200 divided by 2 times 0.1666, and that gives us 600.2 newtons as the force on the car. That's with only a force of 200 newtons being applied to the line. So this is actually a pretty good way to multiply the force that's that's applied. Up here is where I actually used the sine to find the angle, and it works out the same way, except that we're less accustomed to using the sine. So I did it down here using the tangent. I used the sine here because you could use it without finding the value for the x side. But it's easy enough to find the value for the x side, and then you can use the tangent to find the length of it, or to find the angle, I mean. Okay, that brings us actually past the end of this segment of the lecture, so I'm going to have to call it there, and we'll continue on from here next time with friction.